So, session number 4, and today we will consider two topics: how the user equipment acquires the network after power on, and how we can set up data sessions. So those are the two main topics. In case you are attending this for the first time, here is my picture, so that you can relate voice to some image. Okay. And we are recording the session, so feel free to listen to the recorded session in future if you wish. A couple of simple questions before we dive into the details. Please tell me what kind of work you are currently doing. I will give you about 30 seconds. And please participate in all the polls. And there is no limit on the number of questions that you can ask. So we would appreciate you typing in the questions. We'll periodically unmute the bridge, so you have one more medium that you can use to ask questions. Okay. About 40% customer support, 16 systems engineering, 33% test integration. Okay, very good. What kind of details would you expect today? And again, I will try my best to conform to the majority here, but if you are in a minority, no problem. Okay, just ask for additional information if you need. Okay. We want to make sure that we meet everyone's requirements. Okay, so about 70%, 75%. So about 75% are interested in few details, and about 25 want a lot of details. Okay. So for those 25% folks, please ask questions. Okay, that will make sure that you do get what you need. Okay, and for those 75% folks, please have patience. We need your cooperation, because sometimes we may need to dive into the details in response to some questions. Okay. So again, thank you for your cooperation in that regard. Okay, one more question, and then we'll start covering the material. I will give you about 20 seconds to finish up this one. Okay, close to 100 LT and 1X and X video. Okay. Again, thanks for participating on the poll, all the polls so far. And we really appreciate your feedback. So please participate in all the polls. And I may ask you some additional questions. And in that in response to that question, you can type in your answer, again, using the questions box that you have. Okay. Okay. You should have the PDF file that contains the acronym. Okay. So, again, this set is for today's session, we have a separate PDF file that contains the acronyms for the entire Bootcamp series. So you should have access to that. So feel free to have that handy. And I'm always here if you have any questions. Okay. So first topic today is our system acquisition. So let's take a look at that. Okay, so basically our user equipment, we are turning its power on. So at that time, what does the UE know? So every UE knows its own capabilities. Okay. And what kind of PLMNs, public land mobile networks. For example, if it's a Verizon subscriber, the PLMN would be Verizon PLMN. If it is AT&T subscriber, AT&T PLMN would be the preferred one, something like that. Of course, the UE knows what frequency bands it is able to support. To communicate with the network, the UE needs to know several things about the network. For example, how much bandwidth is being used. Okay. So if you recall, we may have as little as 1.4 megahertz spectrum, as wide as 20 megahertz spectrum. Okay. That's the bandwidth. And typically, initial deployments would probably have 10 megahertz bandwidth for the downlink, 10 megahertz for the uplink. That's the most common deployment that we should see, at least initially. Okay. So we need to know such information about the system. We need to know which PLMN is currently available to us. Okay. In 1X, we have a list of carrier frequencies, so-called PRL, preferred roaming list. I have personally not seen any specific term that is applicable to LTE, but we just say that it's programmed with list of PLMN and so on. Okay. Yeah, but the idea is the same, that we will have a list of frequency bands and the PLMN. But I have not actually seen specific term for that. Okay. Thanks for your question. So in response to your questions that are coming through the questions box, I will try to send you acknowledgement by tapping in OK or K, something like that. And whenever a suitable opportunity arises, I will answer your questions. Okay. So keep your questions coming. Here are the main steps of system acquisition. So after power on, the UE will first achieve slot synchronization, and basically at this time and frequency synchronization. Okay. And very quickly, let me just draw a picture to refresh your memory. So basically in UMTS LTE, we have 10 millisecond frame, radio frame, and we have divided that into 10 subframes. Subframe 0, subframe 1, up to 9. So that will be 1 millisecond long subframe, and then within a subframe we have 2 slots. Okay. So one time slot here, other time slot here. So that would of course be half millisecond long. So that is the structure that we have for LTE air interface. So we are first achieving the slot synchronization, meaning we will know the boundaries of the slot, when the slot starts, when it ends, and so on. After we are done with that, the next step is frame synchronization. So here we'll identify the boundaries of a frame. Basically here we will use the help of primary synchronization signal. Here we can use the help of secondary synchronization signal. Okay. And the byproduct of this operation is that we will know the basically cell number 0, 1 or 2 within a group. And once we look at the secondary synchronization signal, we will know the group number, cell group number. And we have 168 such groups. And once you have the cell number and the group number, by combining these two pieces of information, we will be able to figure out that, we are talking to a cell that has identity number 20. Okay, so total of 168 multiplied by 3, 504 cell IDs. Okay, so that's the information that we automatically collect after achieving slot and frame synchronization, after observing primary and secondary synchronization signals. Once we know the cell ID, we are able to descramble the broadcast channel. And basically, the first piece of information about the network comes in the form of master information block. So physical broadcast channel carries so-called master information block, and that will tell us, for example, how much bandwidth we are using for the downlink. Okay. So now, for example, the UE will know that I am in a cell that is using 10 megahertz bandwidth for the downlink. And then we move forward and collect additional pieces of information about the system, and they arrive in so-called system information block. I'll give you some examples of SIP little later. But basically we learn about the system. Now we are ready to contact the network. We will set up a signaling connection between the UE and the E node B. And that signaling connection is called this RRC signaling connection, radio resource control. So that is a signaling connection. Once you have that signaling connection, you can reliably exchange signaling messages between the UE and the E node B. And we can do, for example, so-called initial attach procedure. We will see how to do that. Okay. So we are able to basically exchange messages using this RRC connection. So until you have this RRC connection, you cannot exchange signaling messages with the network. So that's very, very important to establish the RRC connection. So in today's session, we'll take a look at all these various steps. Now we'll take a closer look at the synchronization process. We covered that in session number 3, but basically the primary and secondary synchronization signals, they will consume the center 72 subcarriers, okay, and corresponding to 6 resource blocks. So at certain time periods, during specific time periods, basically we will see that there are primary synchronization signal, secondary synchronization signal, and the broadcast channel present. So not all the time, but during specific time periods, those signals and the channel exist. but they are basically in the center portion of the spectrum. So if you want to look at primary signal, secondary and broadcast channel, you do not need to know the system bandwidth. We may be using 20 megahertz bandwidth or 10 megahertz, doesn't matter. For the UE to detect these signals and the channel, it is just observing the center portion of the spectrum. So we do not need to know the system bandwidth at that time. After we look at the broadcast channel, and specifically after we process the master information block, then only we will know that we have certain bandwidth being used inside that cell. So that's the beauty of this signal, that no need to know the system bandwidth before we look at the broadcast channel. And very quickly, we already covered that in a fast fashion. So basically, primary synchronization signal we look for first, and there are only 3 sequences, so we will know the cell number at that time, cell number within a group, in some group. And then we look at the secondary synchronization signal, 168 sequences, so we know the group number. And as I mentioned earlier, the combination of the group number and the cell number, right, will tell you the physical layer cell ID. So if my group number is 10 and cell ID is 2, then my physical layer cell ID is 32. Okay, that is the idea. So we have 504 such cell IDs, 0 through 503. The reason that it is important to know the cell ID is several channels are scrambled using the cell ID. We have frequency hopping, that is a function of cell ID. So where are the reference signals, so-called pilot or reference signals? Again, function of cell ID. So very important to know this physical layer cell ID. Okay. Now the UE is trying to learn about the system. So we have looked at the primary, secondary signals, and then we can process the broadcast channel and some other stuff. And when we do that, this is what we are trying to collect. Master information block, okay, that will go over the physical broadcast channel, and it tells us about the system frame number and the bandwidth, how much bandwidth we are using. And you can think of PN offset of 1x and 1x CVDO as being equivalent to the cell ID here. So that's the equivalence between two technologies. So this is how we can separate one cell from another cell based on the cell ID. Okay. So it is like pin offset in 1x NDO, and it is like primary scrambling code being used in basic QMTs. Thanks for your question. Okay, so we are getting master information block first from this broadcast channel, and then information would also come in many system information blocks. And here we are giving you all the types that have been defined. So for example, type 1 would tell us that, oh, this is the identity of the PLMN, public land mobile network. So in case of Verizon subscriber, this would indicate Verizon Wireless as the service operator. And let's say we want to figure out who exists in our neighborhood. Maybe there is some 1x EVDO in that neighborhood. So high rate packet data, that's 1x EVDO. So the neighbors of 1x EVDO. So here we will give P and offset 100, 200, 300, etc. So we provide this kind of neighbor list as part of one of the SIPs. Okay. So many SIPs are being defined. So we have listed here all the types that have been defined by the LTE standard. And if you are more interested, you can look up in this specification and you will get additional information. But basically, the information about the system is within those system information blocks. And now how do we know where to find the system information block? So let me give you a simple example. Okay. Now before I move forward, let me ask you a question. For the downlink, let's say I have this UE. Okay. UE number 1, and I have another UE here, UE number 2. I want to separate these two UEs on the air interface. So there is some specific identity that we allocate to the UE. That's how we separate one UE from another. What is the name of that identity? Okay, starts with C. How do we separate one user's radio connection from another user's radio connection? This is for dedicated connection. You can type in your answer. Okay, very good. CRNTI, perfect. Thank you for your answer. So CRNTI, cell radio network temporary ID. So this is how we separate one user from another. So this user, let's say we give CRNTI 0010 or something like that. CRNTI is a 16-bit number. Then another user, I will give another ID 11001, whatever, something like that. Okay. So CRNTI is what we use to separate two users. So when we want to convey resource allocation, then we will use the CRNTI as our identity for allocating resources to different users. So when we want to send system information block, what I will do is I will use an identity called SIRNT. System information radio network temporary ID. So in early part of the subframe, I will have the control channel, let's say symbol number 0. We have control channel, let's say I'm trying to find, okay, very good. I have this control channel. And I will say that physical resource block number 0 carries some system information block. So I am indicating PRV number 0. Okay. So that is the resource allocation for SIP. So this message will have CRC, then we will mask CRC with SIRNTI. Okay, and now that message is inside the control channel number 1. So control channel number 1. Then there is another control channel, maybe here. but that control channel is for some other user. Control channel 2 for downlink allocation user number 1, something like that. So we have different control channels for different purposes, different UEs and so on. So now these UEs will look at the control channel number 1 and they will try to match CRC with several options. They will try to match with SIR and TI, and they will try to match with their own CR and TI, the dedicated. So here both of them will find a match with SIR and TI. That's common. That's common. So everyone knows about SIR and TI. So both of them will find a match, and then they will know, oh, since this is SIR and TI, system information and TI, this physical block number 0 is now carrying some system information block. So basically that block would be here. So that is the system information block, and that would contain information about the system. So in summary, the control channel CRC is masked with SIR and TI. That's how all the UEs know that, oh, there is some system information block in the PRB number 0 at that time, inside that subframe. Okay. And we can send a variety of system information blocks, and we provided here the list. So let's summarize. Basically, the E node B will send out the system information periodically with control channel indicating where the SIB information would be located. So the actual SIB information is on the downlink shared channel. So whatever we drew here, okay, let me go back for a few seconds. This one actually is part of physical downlink shared channel. So some part of the physical downlink shared channel, and specifically physical resource block number 0. So that portion of the physical downlink shared channel is used for SIB at that time. But it is dynamic. Okay, it's dynamic. Okay. And it is up to the E node B where it wants to put the system information. Okay. So we can share this 300 megabits per second physical downlink shared channel among many users. So we can send a page message, we can send traffic, signaling message, a lot of things can be done. We have good question. Are these SIBs repeated periodically? Yeah. So for example, we can say that, okay, every 100 milliseconds, we will send system information block number 3. So every 100 milliseconds, we will see that. Okay. And it is up to the E node B to decide that. Typically up to the E node B. So they are not present in every single subframe, but they will be present in specific frames determined by the E node B. There are some rules for the master information block and SIB type 1. So for example, you will see that master information block is sent every 40 milliseconds. Okay, so we repeat that 4 times. So basically 1, 2, 3, and 4. 4 consecutive frames will give you 40 milliseconds, and then another set of 4 frames, right, that will again have master information block. So we have that rule for master information block. But How frequently we can send type 8? Right? That would be up to the E node B to decide. Again, thanks for the question. Anytime you want more explanation, additional details or whatever, just ask a follow-up question. Or you can use the audio bridge when we unmute the bridge. Okay. But if I do not see a follow-up question, then I will assume that you got your answer. Okay. And SFN is the system frame number. So it is the number of the 10 millisecond frame. So basically frame number 0, frame number 1, frame number 2, 3, etc. So every 10 millisecond frame has a specific number associated with that. Okay. So if our UE wants to find out physical layer cell ID, what is good enough? Actually, if you attended yesterday's session, then it will be easy for you, but hopefully you have been paying attention. So you should be able to answer this without any problems. What signals are good enough? Okay, for the UE to detect the physical layer cell ID. Remember, we need the cell number, we need the group number. Who gives you the cell number, who gives the group number? If you think along those lines, you will get the answer. I will give you, let's say, a couple of minutes to think about this. So what does primary signal give you? What does secondary signal give you? Think along those lines. And if you do need, you can refer to the PDF file that you have. Hopefully you do not need that, but feel free to use that also. Okay, let's share the results. 88% gave the correct answer. So yes, we need both the primary and secondary synchronization signals. Primary signal will give you the cell ID 0, 1 or 2. Cell number within the group 0, 1 or 2. And the secondary synchronization signal gives us the group number. So the combination of the cell number in the group and the group number will give us the physical layer cell ID. So we do need both the primary and secondary synchronization signals to be able to calculate the physical layer cell ID. Thanks for your answer. Okay, let's move forward. Okay, so now we know how the network acquisition occurs. Basically, we need to look at the synchronization signals, the broadcast channel, and look at the downlink share channel to retrieve system information block. So now we know about the network. Since we just turned on the power of the UE, the network has no idea that we exist. In that case, if someone wants to contact us, there is no way for the network to page the mobile device. So that's why we need to carry out the attach operation. So basically, by performing this network attach operation, the UE is telling the network about its existence, and in future, we can contact the UE by sending a page message. So that's the basic idea, letting the network know about the UE's existence. So that's what we will take a look at. How to execute this attach operation. We need to send the attach request message. That is our first step. However, to send this kind of message, we need the signaling connection between the UE and the E node B, that is the RRC, radio resource control. And in case you have forgotten, let me quickly refresh your memory. So between the UE and the E node B, we have UU interface, right? Air interface. And the air interface has several layers. We have the physical layer, MAC, RLC. This is like RLP of 1xc video. Then we have PDCP, and we have RRC. Okay. So these are the layers that we have in our protocol stack. So the traffic basically will pass through these layers, and a signaling message will pass through all the layers. Okay. So this RRC, radio resource control, is our topmost layer, and that is helping us with signaling messages. Okay. So layer is also called layer 3 signaling. So physical layer is layer 1, and everything else here layer 2, and this is layer 3. So that's what we are talking about. So we are establishing the connection between the UE's RRC layer and E node based RRC layer. So that would be the first step whenever you want to set up a call or whenever you want to do operations such as network attach, RRC connection. Now we have the signaling connection between UE and E node B, and we'll be able to reliably exchange the rest of the messages. So using the RRC connection, the UE sends a request. E node B says, okay, this UE is trying to contact the network. Let me select a suitable MME, mobility management entity. So let's say we have this E node B connected to MME1, MME2. So E node B has picked our MME number 1. So now we will set up a signaling link between the E node B and MME number 1. That is the S1 connection, S1 MME interface. That is the control plane between the E node B and MME. Okay, so we set up that S1 MME link, and we'll forward this message attach request to the MME. Then MME will work with HSS on one end and UE on another end here, so that we can take care of authentication. We want to make sure this is a valid user. The user will make sure it is a valid network. We have mutual authentication in LTE. As part of the authentication process, toward the end, we will generate some sort of security keys. And the reason for that is that will prepare us to do encryption in future if you want to do. Okay. So that's why we generate some sort of security key. MME will now pick a suitable serving gateway and PGW, PDN gateway is your PGW, SGW and PGW for that UE. So in this example, we have picked this serving gateway, MME has picked this PGW, and now we will establish a default bearer between the UE and edge of the network, which is PGW. So this is our end-to-end default bearer. And the reason that we are establishing this default bearer is we want to give the user always on experience, always on. So the user feels connected to the network all the time. Also, it is possible for us to allocate the IP address to the user during the attach operation itself. And specifically, PGW allocates IP address to the user equipment. The final step is for the network to send attach accept message. And that attach accept message is sent in one of the RRC messages, such as RRC reconfiguration message. So basically we are responding to the attach request that our UE had sent, and that's why we are sending attach accept message. We have a question. So do we have to give IPv6 address? No, not necessary. We support both IPv4 and IPv6. So not a requirement in LTE. Both are supported, but up to the service operator what they want to use in their network. Good question. So we looked at the high-level view of how to carry out the attach operation. In the next few minutes, we will take a look at all these steps in more detail. Okay? But before we dig deeper, I just wanted to give you a high-level view. Okay? Okay, we have one more question. Who sends the accept message? MME. Signaling is the responsibility of MME. So between the UE and the EPC, Evolved Packet Core, whenever we do signaling, that is actually between UE and the MME. MME is responsible for all signaling. Okay, a good question. So attach accept is created by MME. Okay. Keep your questions coming. It will not only help yourself, it will also help your colleagues. Okay. And in case I do not know the answer, it will also help me. I will try to find out the answer, and that will increase my knowledge. So win-win situation. So keep your questions coming. What is the purpose of RRC reconfiguration? Oh, actually in LTE, we have tried to reduce the number of signaling messages. If you look at the basic UMTS RRC specifications, is about 1,300 pages long, very, very long document. And in LTE, it's a couple of hundred pages. So we have tried to streamline the messages. The basic UMTS is too complex. lot of things. So here we are trying to simplify. So RRC reconfiguration is one such simplification. So RRC reconfiguration will help us send many different kinds of information. So when we want to send a core network message such as attach accept, we can put that inside RRC reconfiguration. So in this specific slide, the RRC reconfiguration carries the attach accept message that is coming from the MME. Okay. Good question. Okay. So as I mentioned, we will take a look at all these steps closely now. Okay. We know the high level view now. Time to take a closer look. Okay. So we said that if you want to contact the network, right, we need to send this attach request message. And before we can send attach request, we need to have some sort of RRC connection. So this is how we can establish RRC connection. Since we have just turned on the power, we have no dedicated resources given to us. So we have to rely upon the common channel. And in the uplink, the UE has access to the random access channel, physical random access channel. So the UE will pick some random sequence, which is your preamble, random access preamble. There are 64 sequences available, so UE will randomly pick one of the sequences using the random access channel. The E node V is looking for some preamble, so it is always searching in that uplink that is anyone sending me any signal or not. So in this case, the E node V has detected the preamble, and that's why it is sending the response, random access response. That response will go over some physical downlink shared channel. Okay? And the existence of that will be conveyed by the control channel, and the control channel will be masked with this RNTI, random access, a radio network temporary ID. Okay? So let's say we send, okay, do not worry about F frequency ID, this is 0 for FTD, and this is the subframe number. So if we have sent preamble in subframe number, let's say 5, then RNTI becomes 5, same as the time ID or subframe ID. So the control channel would indicate that, oh, there is some random access response, okay, on physical resource block number 2, let's say, okay, and it will convey that by masking the CRC with random access RNTI, and that number will be 5. So RNTI will be 5. So if we are a UE and we send the preamble in subframe 5, then we look for the CRC match with number 5. That our CRC will be matched with RNTI of 5. Okay. Not only that, we know that which preamble sequence, right? Which random sequence. So let's say we picked the random sequence number 30. Okay. So that ID will be available, 30. Now we know that, oh, this is in response to my preamble because I sent preamble number 30 inside subframe number 5. So it means that this random access response is for me, not for some other user. That's what the UE thinks. Okay. Okay. So when we look at the random access response, we will get some grant. This grant is basically tiny bandwidth given to the UE so that UE can send some uplink message, the dedicated bandwidth for the user. Also, we will allocate CRNTI because for every UE with a dedicated radio connection, we must allocate CRNTI, cell RNTI. So that's what we are giving also as part of the random access response. Not only that, we also provide some adjustment, timing alignment. So we will tell the UE, advance your timing or delay your timing so that the next time UE sends a signal, it is in perfect synchronization with all other UEs inside that cell. We have very good question. Could there be collision on the random access? The answer is yes. So maybe two UEs picked the same random number, 1 out of 64, and they send that random number in the same subframe, maybe subframe number 5. So yes, it is possible that there is collision. Okay. And now we will see how to take care of it. Okay, so yes, it is possible. Yeah, good question. So we got this one. And now, using this tiny dedicated bandwidth, the UE is sending a message such as RRC connection request. RRC connection. And inside that message, we will provide ID such as such as IMSI, or sometimes random number, depends, random number, something that is related to the core network. Okay, related to the core network. Okay. So non-access datum, this is an example of a non-access datum ID. It's basically the original ID of the UE called IMSI. In the past, if we have contacted the network would have given us so-called STIMSI, temporary mobile subscriber ID. So these are some examples of that. Or there could, if we do not have such ID allocated, then we will use some sort of random number. So this would be, if I have not forgotten, I think 48 bits long. 48 bits. Basically some sort of ID that will identify that specific UE. Okay. Now, the E node B will respond to our RRC connection request. So it will send contention resolution, and here it will indicate, let's say STIMSI was X. STIMSI X. So now we know that we have successful RRC connection established. No problem whatsoever. One student asked the question, could there be collision? So let's take care of that scenario. So let's say and this will also answer another question that we got. What is the difference between random sequence and preamble? So let's say this is UE number 1 and this is UE number 2. Both of them want to contact the network. Okay. So this guy says, okay, let me send some okay, preamble number 30. So UE1 randomly picked this number 30. So 0 to 63, 64 possibilities. And it will send in subframe number 4, let's say. So here we have this 10 millisecond frame. Inside that we have subframe 0, 1, 2, 3, 4, up to 9. So this UE1 has said, okay, let me send that in subframe number 4. It will send preamble number 30, some sequence inside subframe number 4. Then this UE2, so it generates a random number, okay, which is this again same. By coincidence, it picked the same number 30. And it says, oh, let me send that in subframe number 4. Okay. So by coincidence, both these UEs 1 and 2, they have picked same random number 30, preamble number 30, and both of them are sending the preamble in subframe number 4. So the base station says, okay, I have detected random access response. So it says I have detected RARNTI equals 4 because that is exactly the same as the subframe number. And I have detected preamble number 30. So now both the UEs will think that, oh, this is my response. So they said, okay, let's send a message, RRC connection request, for example. And UE1 will now send its string equals X. However, UE2 has another identity. So it will send RRC connection request. But it has another ID, right? That network has allocated to the UE in the past. Now the base station will detect one of the two signals. Whoever is closest will probably be detected successfully. And now, in the contention resolution message, it will indicate string equals X. Then it means that UE1 RRC connection successful. And UE2 looks at this contention resolution message. Oh, this is not my ID. So UE2 says, oh, RRC connection failure because of contention. So then it will retry. So now we know how we can resolve potential conflicts. Now, is a subframe number also randomly selected? In general, yes. In general, yes. Normally, if you are a UE, you will just try to send the random access preamble as soon as possible. So it is possible that two UEs woke up at the same time and they are quickly sending out the preamble in some subframe number. So in general, subframe is randomly selected because different UEs can wake up different times and they can start accessing the random access channel at the same time. Or different time, depends. So for all practical purposes, you can think that subframe number is also randomly selected. Okay. But if you have additional questions, no problem. We will take a short break soon. And when we unmute the bridge, you can ask additional questions. Okay. So that's what we have regarding the random access process. Okay. So basically, once we are done with this overall process, then we have established RRC connection successfully. Here we had a possibility of collision. Right? That's why we say it is contention-based random access. There is something else called non-contention-based random access. So basically here what will happen is during the handover, we will tell the user that here is the preamble sequence number for you, and no one else will use that preamble. So in that case, it is non-contention based because no other UE is allowed to use that specific sequence on the random access channel. So it is possible that we have that kind of scenario, but that normally happens during the handover process. How many UEs can the E node be support? Is it limited to 64 for access only? Yeah. So yes. So within one subframe, yes, we can have up to 64. So within 1 millisecond interval. So let's drop it. So we have 64 potential sequences. Right. So in 1 millisecond subframe, since we have 64 sequences available, then up to 64 UEs can, maximum of 64 UEs can do a random access during that subframe. But if you go to the next subframe, another set of 64 UEs can potentially access, and yet another set, and so on. But within 1 millisecond subframe, yes, up to 64 UEs can simultaneously access. But remember, these are all the UEs generating these random numbers, right? They're picking random sequences. So you will start seeing collision much before you reach 64. Okay. But yeah, up to 64 can simultaneously access, up to 64. In practice, that would be much lower, but up to 64. 64 is the maximum in 1 millisecond subframe. Thank you for asking all these good questions. Okay. So we know all about this random access, and we have established the RRC connection. If you want a little more information, here is that sequence, let's say preamble sequence, okay, 1 out of 64, and the random access channel itself occupies 6 resource blocks consecutive, but it could be anywhere. Could be anywhere in the spectrum. Doesn't have to be center part of the spectrum, left or right part of the spectrum. Anywhere. Wherever the E node B chooses, it can exist there. Okay. Okay. And how long does the preamble last? So it could be just within one subframe, or it could span multiple subframes also. It just depends. LT is very, very flexible. So we have preamble formats defined in the standards, and based on the preamble format, we will choose certain number of subframes. So typically, I would expect it to be one subframe. Okay. So as part of the random access, we mentioned that we are establishing the RRC connection. So we are sending this RRC connection request, and that is supposed to be going over so-called SRB0. SRB is nothing but the signaling radio bearer. Signaling radio bearer and the data bearer or the traffic bearer. So we have two main types of bearers. Here, as the name suggests, we are doing only signaling messages. And here, as the name suggests, we are able to exchange the user traffic. So whenever we are sending a signaling message, we are saying that, oh, we are using some sort of signaling radio bearer. So SRB number 0 is for this common channel in the uplink, the RRC connection request. And here we will provide some sort of identity from the non-access setup. So if we have a valid STMZ, we will use that. Otherwise, we'll generate some 40-bit random number. Okay? One of the two. And we will indicate to the network why we want to establish the RRC connection. So we would say something like initial attach or something like that, that we are trying to do this kind of operation, and that's why we want to establish the RRC connection. eNode B responds to the connection request by sending the RRC connection setup message, and inside that we will include the resources so that we can set up bearer number 1. Okay? And using that signaling radio bearer number 1, we are sending a message, RRC connection setup complete. So connection request, connection setup, and connection complete. So these are the 3 signaling messages that are exchanged between the UE and the network so that we can successfully establish the RRC connection between the UE and the eNode B. And as part of the complete message, we would tell the network what PLMN we have selected. So Verizon Wireless PLMN would be one example. If we have a valid information about some MME, we will say that, oh, I have registered with some MME in the past, and here is the identity of that MME. So that would be MME group ID, and within that group, what is the MME code? So the group and the code within the group. This is the mobile country code, mobile network code. So hopefully the acronyms that we have in the PDF file should cover all this. But in case you face any problems, just let me know. And then we can send something related to the non-access setup. Non-access setup is basically related to your core network. So here we are sending the message attach request. The reason that we are calling it NAS information is our eNode B does not process this. So eNode B, whenever it gets this NAS information, it will just transfer it to the MME. So the NAS information directly goes to the MME because the attach request here is for the MME. Core network is responsible to process such messages. The radio network is not responsible for attach operation. So it is just forwarding the non-access data message that it got from the UE to the MME, and MME will process that attach request message. So in summary, before we can set up the call or before we can do attach operation, first we need to establish the RRC connection. And this is what we are doing here, establishing RFC connection. Let's have a short break, and once we come back from the break, we will unmute the bridge so you have an opportunity to ask questions. So during the break, think about what questions you would like to get answered. Okay. So 10-minute break.